Okay, awesome. So we'll start the seminar now. So welcome all to the seminar. Today we have Professor Michael Carbin with us. Michael Carbin is an assistant professor with us at MIT ECS department and a PI at CSIL. He leads the programming systems group and investigates the semantics, design, and implementation of systems that operate in the presence of uncertainty in multiple different domains. They analyze systems that perceive under uncertainty in their environment, systems such as neural networks and approximate transformations with uncertain implementation or execution under on unreliable hardware. Professor Carbin has also received multiple awards, such as the Sloan Research Fellowship, a Facebook Research Award, a Google Faculty Research Award, and an SF Career Award. He earned his bachelor's in computer science at Stanford and a master's and PhD with us at CSIL. Today, he will talk about the lateral ticket hypothesis, which won the ICLR 2019 Best Paper Award and has influenced how many of us in the field think about neural networks. Welcome to the seminar.
Thank you, Ferran. Thank you for inviting me. I'm happy to be able to finally join up. It's been a tumultuous time. Ferran's been trying to get me to speak for a little bit of time, but I have a well, almost 4-year-old. Kept me very busy now that school has been canceled. And it is possible she may walk into this talk at some point in the hour. So please bear with me if that does happen. But anyway, so today I'm going to be talking about some of the fantastic work that's been going on in my group. Particularly, led really by my student Jonathan Frankel, who is here on the call, who can, if there are very, very low-level detailed questions that come into play, he may be, at the reins to be able to help out with those. But so this work, as Ron had noted, we've been very fortunate to find some very interesting observations that demonstrate that though we have become accustomed to training these very, perhaps hilariously large neural networks, there seem to be these small subnetworks within them that do train just as well. And so to get onto this, I don't need to belabor this point about neural networks being large, or why they're large or their capabilities, but I will just a little bit, just to bring it in, right? Where if you look at, some of the latest results that we're seeing in GPT-3, which I think at this point, many of the people on this call have seen in one way or another, either through reading the paper, being on Twitter, being within some rumor mill, whatever it is, right? There's a lot of hype about some of the interesting results that have come out of GPT-3. And of course, it is not alone, actually, in ways such as how expensive it actually is to train. It is quite a very, very large network. So it not only takes quite a bit of data, so it's trained on 500 billion tokens, but it's also, so estimates right now, and I've seen these estimates range all over the map, but it's estimated to take about $4.6 million to train this. I think that's approximately around hardware costs alone. But if you start to incorporate the actual expertise that you need to train this, person expertise you need to train this model, start to include salary costs, you're getting up into numbers where I've heard, upwards of $20 million. So this is, quite a beast. This is some of the computations that we're starting to see are truly starting to be, coming from the system side, being at this supercomputing scale, really, where these are some of the largest computations that we may in the future be running. And in fact, again, just the hardware costs, the models as they are now. And if you look at the GPT-3 paper, you can tell that although there are 175 billion parameters in this model as it is right now, they're already looking towards 1 trillion. And I certainly know people inside of Microsoft who are looking at those targets and beyond as well. So we should expect, while now, these are already quite large models, exceeding the capacity of single machines and even some of the distributed setups that we have, they're just going to continue to get larger as people look for better performance. So, to our work on the lottery ticket hypothesis, what we've been doing is investigating opportunities where perhaps we can train smaller models that still do just as well as, for example, this large GPT-3 counterpart. And so where we started this type of investigation, where I want to start this talk, is by looking at some background work in making large networks small, but for the purpose of inference. So you train your model, you're going to do pruning, which I'll talk about and explain. And then as a result, you'll be able to get the smaller model that you can use for inference, right? Now in our work, we're interested in, can we also accelerate training? But I do want to start out first talking about inference. So pruning. So if you haven't seen this before, hopefully this is a gentle introduction. But the idea behind pruning a neural network is that we can take these large networks and throw away parts of them yet still have them behave just as well, at least for inference purposes, right? And so the history of this type of work goes back, several decades. It goes back to some of the work in the 90s and some work that Jan LeCun and his collaborators had done, but there's actually, many pieces of work that came out around that time, looking at various different ways of trying to reduce the size of the network. I think in this particular instance, they got, just the perfect title with optimal brain damage for the type of work that they were looking at for this pruning work. But more recently, Song Han, who's now joined us here at MIT, revived some of these old techniques and demonstrated that they are actually quite practical and effective for reducing the size of more modern neural networks. So this was a paper that came out in 2015. And so to explain how this technique works, I'm going to go through just a very simple cartoon animation where, and it's not listed on this slide, but let's start with step 0, which step 0 is you have your neural net architecture and then you randomly initialize it. And that's usually our step 0 in this modern day and age. Now, step 1 is we're going to train this using your standard optimizer setup, however you prefer to optimize this network to get it to the best accuracy that's available to you at the time, right? Ideally, no changes. So now in the next step, now we're going to start to do pruning. So we're going to remove some of this superfluous structure. And so what is structure and what is superfluous? And even what does remove mean? These are things we all need to give definition to. So structure. So there are many different structures that we can think about in a neural network, such as weights, neurons. In the convolutional setting, we can think about filters or channels. In this work, I'm going to talk primarily about removing individual weights. And by removing, what I mean is setting these weights to 0. So I can take a network and I can remove a weight by setting one of those weights just to 0. And we're going to consider that to be pruned from the network. Now, superfluous. Now, which networks or which weights, which structures do I actually want to remove? So again, in the literature, there are a wide variety of techniques for trying to assess the importance of a particular weight or structure to the overall behavior of a network, ranging from just looking at the magnitude, so the magnitude of the weight, for example, the gradients that fall upon that particular structure, the activations that are associated with that structure. So in this work, I'm going to talk about the magnitude. So the magnitude of a weight. And our pruning technique that we're going to talk about and we use primarily is magnitude pruning, or what we do is we look at a network at some point in time and we're going to remove the lowest magnitude weights. So that's going to be our pruning heuristic, primarily under study in this talk. But as I mentioned in the literature, there's just a whole basket of techniques that are out there. And in fact, Jonathan, along with a few other people at MIT, did a nice survey paper this past year in MLSost on 80 different techniques that are on the literature and how to organize some of that space and what's out there, because there's just quite a bit of what can be done. But magnitude pruning for weights is a very reliable and robust technique has been posed, back in the times in the 90s and seems to have survived even until now as a very effective technique, despite all the other advances that are out there. So that's our step 2. So we're going to remove this. So as we move through our cartoon, right, we're getting to our blue network that now has been trained and we've removed some structure. Now in our green network, what is this last step? So the next step number 3 is to fine tune the network. So when you remove these structures, when you enact this pruning on the network, even after training, immediately the test performance of the network will drop, right? And so what you need to do is figure out some way of actually recovering that accuracy. And so typically what you do is you will take additional data, apply your particular optimizer that you've been using before, and then recover the accuracy of the network. So that's it, right? That's your basic setup. Now, you can modify a little bit more where you can do this repetitively. So these last 2 steps 2 and 3, where you can repeat iteratively and get to a smaller and smaller network through a number of different steps. Now, what are the results? So this is just an illustration of the graph from Song's paper back in 2015. But the important thing to notice here, so I've got these 2 columns highlighted. So we have a variety of different networks. And in this left column, we're looking at the test error. And what we're seeing is, so this ref line versus this prune line, this is the difference. These are the measured errors of the reference full network versus the prune network. And what we're seeing across these different networks is that there's very little change in the accuracy of the network. And on the right side, we're actually seeing for the pruned row, we're seeing how much smaller this network, this pruned network is. So we're seeing networks that do not change, that are roughly the same accuracy as the original network, but over an order of magnitude smaller. Right. And so this is, a fantastic result when you're thinking about trying to reduce the size of these networks for inference, right? And so techniques like pruning, along with quantization, other compression techniques are used quite a bit, in industry at this time, based on these observations just that you're seeing right now. Now, going back to where we started. So I said that we're interested in training. And as we had brought it before, this $4.6 million that we need for GPT-3, we'd really like to find ways to reduce that cost. Perhaps if we can get this order of magnitude smaller network, we could actually get perhaps order of magnitude reduction in cost, right? So this is one motivation, certainly, for why we would be interested in accelerating training. But there is also other reasons to think about small networks and how they can be effective for other machine learning settings. So for example, federated learning. If you aren't familiar with this concept, the basic idea behind federated learning is that I'd like to be able to collaboratively learn a model based on the data of a wide variety of users, but no user actually wants to fully expose their data. They do not want to send their data, let's say, to a centralized model. So instead, what they want to do is take a model, use their data locally to train that model, and then ship some sort of difference with respect to that centralized model so that those differences can be aggregated and actually applied to the centralized model. Now, of course, if you have a large model, like GPT-3 or some of the state-of-the-art models, this just is not going to work on a small smart device, or perhaps even in the limit setting and on these edge devices, or these small IoT devices, where perhaps we'd even like to do learning. So this is even yet another reason why we might like to be able to train smaller networks and still get high accuracy at the end of the day. And so that brings us to the research question that we started to investigate, I guess now 2 years ago, when this work started to get off and running. And that is, if we, based on these observations, if we can prune models after training, can we just train smaller models from the start, right? And what we can see in this research question is a fundamental distinction between capacity for representation. So these existing pruning results, they demonstrate that it's possible to find a smaller network that represents the same function as these larger networks, right? As evidenced by training that larger network, pruning it, and then fine tuning that smaller one. But it doesn't say, but that's truly different, right? So that's truly different from optimization, where what we'd like to be able to do is take a small neural network from the start, randomly initialized, and train it, right? And so this is where this fundamental distinction is when we're looking at this research question. And in this work, so in this lottery ticket hypothesis work, we've been exploring this research question because what you'll see is that in the literature, this has been a hard question to try to assess, or it's been assessed, but the results weren't so positive. So in particular, what you want to show is that there exists some networks that reliably do train as well as these larger ones, right? So some set of networks in a reliable set of settings, practical, reliable settings. And the first thing that you might think of doing is something like this, where we're going to bootstrap on top of our initial pruning regime. We're going to randomly initialize our full network. We're going to train it and prune that superfluous structure just as we did before. And then, so once we have our pruned network, what we could do is we could randomly initialize that pruned network, because this would now be some evidence that there exists a small pruned network with a given structure. If we were then to train it to convergence, if that worked well, we could actually answer this research question, right? So ideally, this is what you would like to do in a very simple setting, but unfortunately, this actually does not reach full accuracy. So again, just to restate, do your traditional pruning process, get a pruned network, randomly initialize it, and then try to train it again. This actually does not work, and it's been shown several times in the literature. Training a pruned model from scratch performs worse than retraining a pruned model, right? And so here, retraining, what do they mean here? This is clarified a bit more in this following paper. So retraining, it is better to retain the weights from the initial training phase for the connections than it is to reinitialize the prune layer. So this is exactly what I'm talking about. In our traditional pruning setup, we remove this structure, right? But we keep the weights fixed from at the end of training, and then we fine tune from that particular point and go on, right? So what they're talking about here is we remove and then reinitialize, perhaps in the search of this research question, if we can actually answer and find these small neural networks. And if you do this, it just does not work, right? So what's our observation? So our observation is essentially, if you boil it down, so I'll get to explaining how we found this in the technique. But what we did actually find is these weights that were pruned after training using standard magnitude-based pruning heuristics actually could have been pruned before training. And therefore, it's actually, it's actually possible to find a subnetwork of the originally initialized network that trains as well. So let me demonstrate. So to talk about this contribution, let's actually go through the technique and how we modified these techniques to be able to answer this question. So here it is. So iterative magnitude pruning. This is how we're going to describe it. So this is, you can remember this term. It's applied in a few different contexts, but iterative magnitude pruning in IMP, because it's going to show up later on in the talk. But here is the concept. So we're going to randomly initialize the full network. We're going to train it. We're going to prune superfluous structure as we did before. Now, what we're going to do differently versus this hypothetical scenario that we talked about is we are going to take the structure that we find after pruning and backport it. Right? So we're going to take it and apply it back to the original full network that we started training with. Right? And so what does that mean? Well, one, we can do this iteratively just as we did before, but if we get through this process, what we get to is we do actually get to this contribution, which is within a large randomly initialized network, there actually exists a subnetwork that trains just as well from scratch, right? So this is what this technique's actually found. And so to briefly summarize our results, we find that subnetworks that train from initialization to full accuracy at non-trivial sparsities, right? So what does non-trivial mean here? So it's actually, so neural networks, your standard neural network is quite overparameterized. So, depending on the accuracy target that you specify or you're shooting for, even if you're trying to match the accuracy of the original network, you can actually randomly prune, right? So you can randomly prune networks and still match that accuracy. But at the sparsities that we're looking at, for example, 20% of the sparsity of the original network, those random pruning techniques do not work, right? So when we say non-trivial, what we actually mean is as a set of sparsities where randomly removing weights does not demonstrate this hypothesis. All right, so now where have we seen this? So we've seen this at a few different places. So for fully connected networks or MNIST, for CFAR, if you look in our original paper, we validated this for a wide variety of just standard optimizers and different types of layers. A lot of the tricks in the books that you see in modern neural networks. And the key observation here is, again, is if you reinitialize, this no longer works. So again, prune at the end of training, find that mask, but then backport it to the original network that you had. So find that subnetwork of that original network. Right? Now, there are, of course, some caveats here. If we think about our grand goal of trying to accelerate training, one is that we're finding these subnetworks retroactively, right? So we're training it once fully, right? And then pruning and then applying it backwards. And if we do this iteratively, we're actually training it multiple times. So this can actually be quite very expensive, right? But this is for the search of just that research question, that initial research question, trying to demonstrate if this is possible, what are potentially the limits? And then over time, and as we've been continuing to do research, demonstrating that we can get closer and closer to those limits in an efficient way, right? Now, there's another caveat here, which is eliminating weights just outright in an unstructured way does not necessarily equal better performance, right? And so if you're familiar with any of the concerns with building efficient systems for sparse linear algebra, there are a variety of challenges with unstructured sparse representations, particularly how you represent them typically introduces an overhead over a dense representation. And so what this means is that without good software and hardware support, you're not necessarily going to get better performance improvements. Now, I'll return to that very much at the end of the talk and just wrap up in the talking about some of the state of what's going on there. But what we're seeing right now is we're demonstrating reductions in weights, but there's still this open goal of demonstrating a reduction in performance. Right, and then lastly here, so we've been looking at this right now, at least in these results. In this initial paper, I'll say the focus has been for small vision networks and tasks. And so in the next part of the talk, I'll come back to this, where we'll look at larger settings and look at some of the interesting observations and challenges that we've seen in the larger settings. So these are the caveats. Now, let's actually look at some numbers here, right? So what do these look like? So I'm going to show you a few graphs that demonstrate the observations that we've been seeing. Right? So here, what we're going to plot here, this is just going to be a standard learning curve. X-axis is going to be training iterations, and then the y-axis is going to be test accuracy. So we're plotting test accuracy of a network at a given point in training. Nothing too exciting there. And so this legend that I'm going to bring in, what it's going to do is highlight the percentage or the fraction of weights that are remaining for this particular network that we're observing. And this is using our techniques to find a network of a given sparsity or fraction of remaining weights. So here, this blue one, this is going to be 100%. So this is our standard learning curve that we would have. So nothing special here. Again, so this is small Linnet on MNIST. This is just an easy setting to be able to show these types of results, but the general trends that you see translate to even to our CFAR setting. And then, as I said before, I'll talk about the different patterns that we see at larger scales. So first, 100%. So now let's go down to 51.3% of the weights remaining. So this is going to be my orange line. And so what we're seeing here is that the network learns a little bit more quickly, but reaches roughly about the same accuracy. But we've thrown away about half of the weights. Right? So now 21.1%. You can see learns even a little bit more quickly and starts to get even minor improvement in accuracy, right? And so this improvement in accuracy is something that's oftentimes demonstrated in much of this pruning work. And it's something that's interesting. It's an observation that's very exciting that we've seen inside of this work as well, but it's not the major focus here. Really what we care about is that we're learning just as well and we're learning just as quickly, right? Because that's the goal. We want to demonstrate these networks are essentially equally capable as that full overparameterized original network, right? So now, as you can imagine, this doesn't go on forever. At some point, performance starts to reduce, right? And when you get down to 3.6% of the weights remaining, what you can see is we've lost some performance perhaps versus 21.1%, but now we have arrived at a network that is over an order of magnitude smaller and trains just as quickly and to the same accuracy as our blue line, as our full network. Right? So now if you keep going to 1.9, this is of course where we now start to see we no longer have enough capacity to actually learn for this particular problem. Right? So now, I talked about reinitialization, right? This was the key distinction that we were making between what was demonstrated in the previous results, where when people tried to look at similar types of observations, they would just go out and reinitialize a small pruned network, right? So now we can see how this is different. So I'm going to bring in again these learning curves, but now I'm going to introduce a new learning curve, which is going to be a new pattern, which is going to be a dashed line. And so this dashed line is just going to show what happens when you reinitialize at a given sparsity. So at 51.3%, what we can see is there's a little bit of a gap that starts to open up. And actually, as smaller we go, the larger this gap becomes. Right? Now, if I keep going in this particular presentation, it starts to get this format of presentation starts to get a little cluttered. So I'm going to switch to a different presentation to make this distinction more clear. So this is going to be the same network. We're looking at the same network, same data set, but the presentation is going to be a little bit different. On the left side, we're going to plot how long does it take for a network to reach convergence at a given sparsity. Right, where convergence here is going to be given by a fairly simple early stopping criterion that we have. But here, x-axis, percentage of weights remaining, y-axis, how many iterations until this converges. Right. Now on the right side, this is going to be essentially an agglomeration of the types of curves that we saw in the previous slides. We're here, what we're going to show as a function of the number of percentage of weights remaining, we're going to see the accuracy for that given network. So let's actually look at this data. So on this left side here, general trend as we would hopefully expect. So this is using this iterative magnitude pruning technique. So as we reduce the size of the network, moving right, at some point we start to lose representation capacity. Right? In fact, it takes longer for these networks to converge. And on the right-hand side, we see that accuracy starts to fall off. Right? And so this is a general trend that we'd essentially expect to see. Now, if we initialize, this distinction becomes much more clear. Right, so fairly early on, once we're getting to 51.3% or 26%, we're starting to see that these reinitialized networks are really no longer performing as well. They're taking quite a bit longer, perhaps even at least twice as longer to converge, and the accuracy gap is certainly starting to show up. Right. So again, so what did we see in these slides? So based on these observations, we articulated what we've called the lottery ticket hypothesis. And the idea is that these dense networks, these large dense networks that we have, they actually have these small subnetworks that are equally capable. And as I've tried to stress, equally capable here means they reach commensurate accuracy in a commensurate number of iterations. Now, there's some interesting observations where, as we were seeing in some of these results, they tend to learn a bit more quickly. This has been something that's been exciting to see and something that we'd certainly like to investigate, but we there are many interesting observations. One that we haven't gotten the opportunity to fully investigate. And as well as I talked about before, these smaller networks can actually reach improved accuracy, right? But the major focus here is just that we're getting matching behavior from these small subnetworks. And again, that's via this iterative magnitude pruning procedure, where we take the weights or the mass that we learn at the end of training and apply that to the very beginning of training to find what we call a winning ticket, right? So a small subnetwork has been randomly initialized that's happened to have done just as well as the large network. Done meaning if you train it, it will do just as well. Right? So, okay. So now, based on these results, there are actually a number of other questions that have popped up, both from us, but from also other people considering related work in the community. So one, what makes a good initialization, right? So we're actually finding essentially that there is a good sample from a distribution, or particularly the standard distributions that we use for initializing neural networks, right? So specifically, if we take a step back and think about contemporary practices for initializing neural networks, they typically have this distributional characterization. So if you look at, for example, K-mean initialization or Xavier initialization, however you like to pronounce those, what you'll see is that historically they have been focused on essentially normalizing the variance and choosing the variance of the distribution of initialization that you have for an individual layer, right? And so this has been a form of essentially conditioning for optimization, where as a result, these networks seem to train particularly well in aggregate, given a random initialization, but our results are showing as well that there are individual points within this distribution that actually do quite well, quite well and quite better than others. So it's actually a good question of, can we actually find better initializations that are more tuned to finding these sort of winning tickets that are sitting out there. Now, why magnitude pruning? This is another good question. It is actually quite surprising. I think one of the just astounding surprises that we had in the very initial phase of this work was realizing that the magnitude of the weights at the end of training was somehow indicative of their performance right at initialization, or their behavior or their influence in the larger network right at initialization. It just felt like these should be widely disconnected in some sense. So this was quite an interesting, surprising observation that's come up. That's certainly a course of study, and some people started to investigate. Another one is just why weight sparsity. So we've been looking at individual weights that we're pruning, but if you look around in the literature, people start to ask similar questions, where you look at coarser grain structures, let's say at the neuron, filter, or channel level. And if you go take a look at this paper, they'll show that if you start looking at structured pruning mechanisms, where you are throwing away full channels, full filters in a convolutional setting, these types of observations don't show up. And this is this type of improved performance. So if we're going to measure performance of a pruning technique, let's say as sparsity, so the number of rates remaining versus accuracy, what you'll find is that the more fine-grained the technique is, the better trade-offs that you get. Essentially, it's going to be more accurate than if you are looking at more granular structures, right? And so this is something that's shown throughout, and it's definitely something that merits some discussion. All right. And then finally, so this is getting back to our grand goal. Can we find these subnetworks efficiently? Or alternatively, demonstrate that it's actually impossible to find these efficiently at the beginning of training. So we'll return to this top question, or the top half of this last question towards the end of the talk. We'll talk a little bit about the state of what people know about how to find these efficiently at initialization. All right, so at this point, before I change to talking about these larger scale settings, are there any questions that are out there?
I actually have one question. Can you transfer these initializations between data sets? So maybe not the fully connected layer at the end, but maybe the conf layers?
Yeah, so that's a fantastic question. So I was going to return a bit to that question at the end of the talk, but yes, you can. So there's been some interesting work out of Facebook where they picked up some of our observations and asked this same question. Can I transfer a lottery ticket that I found on, for example, CFAR over to SVHN? And Jonathan just put the paper into the chat if you want to look at it. But yes, you can actually do this, depending, of course, on the relationship and the closeness of these two data sets. But there's actually been some preliminary results showing that that is true. And as well, more recently, so we have a NeurIPS paper that's coming out demonstrating as well that you can do this in unsupervised setting for BERT style training, where what we can actually find are essentially general purpose, and I think Jonathan just pasted another one, but general purpose subnetworks that can actually transfer among a wide variety of different NLP tasks. So yeah, so yes, this is actually out there, and this is one way to actually demonstrate some immediate value out of these techniques. So if you actually have a software hardware system that can exploit sparsity, even though it may take you a very long time to find these subnetworks, what you can do is spend all that time once, but then amortize that cost by transferring it then to new problems, right? And one place we've seen this show up is people in industry, for example, use this to keep models fresh, right? So if you're looking in recommendation settings, for example, companies like Amazon and Facebook, they are very sensitive to staleness of their model. Well, they even say, they'll make statements such as, a model that's 2 hours stale based on the data that we have is already going to be losing a significant revenue performance. And so what they do is, we've seen a couple teams, what they'll do is they will train lottery tickets. They will find these winning tickets and then use those to train nightly models based on new data, right? So this is another way. So transferring then to this new distributions of data that are coming in per day. Any other questions?
Hey, Michael.
Yep.
Can I also ask a question? Hey,
yeah.
So the paper you just mentioned, I think the rethinking the value of network pruning.
Yeah.
From what I remember, at the end, they also did some experiments where they also compared to the lottery ticket on unstructured pruning. Mm-hmm. And I wasn't sure anymore, but I think that they found for some settings that also random initializations work. Would you be able to comment on that?
Yeah, so this is the next phase of the talk, in fact, right? Mm-hmm. Where once you start getting up to larger settings, these observations start to change a bit. And it's required us to move from, let's say, just at initialization to shortly after initialization. That's the summary, but I'll show you how we found that and the techniques that we've used to diagnose that and the new techniques that we've developed in response. Yeah.
Cool, thanks.
All right. I think on that one, why don't I go ahead and then move forward and get to it. Okay. So as I had mentioned, smaller scale settings. So, I showed some results just on MNIST, for example. But when we start to look at CFAR or moving up to ImageNet, the picture becomes, more nuanced. There's more detail to it. So let me show you some results. So I flashed, just the heading of our ICML paper. So this is work that we just did to actually understand what's going on at these larger settings. But many of the results, I'm just about to show, these are results that we actually had in our original paper as well, showing that at these scales, something different was actually going on. And so what different is going on? So let's take a look. So what I'm going to show you here now is going to be similar curves, except now for VGG 16 on CFAR 10. So now we are orders of magnitude larger in the number of parameters that we're looking at, and we're also looking at a much larger data set. Right? So this is the behavior if we apply this procedure that I just talked about in the last part of the talk. We're applying iterative magnitude pruning to this network on this data set. And this is the line. Again, x-axis, percentage of weights remaining, y-axis, test accuracy. All right, so now remember our pointer distinctions, we're comparing against what happens if you do reinitialization. Well, if you do reinitialization in this setting, you see something that looks pretty similar, right? We're not seeing that gap. Right, now what I'm going to do here though, right, is first flash a couple papers and then change those ever so slightly, right? So as Lucas had pointing out, this is something that had showed up in rethinking the value of pruning, something that we were already aware of and we're working on, and they did some replicative studies to figure out what was going on in their end. And as well, there's some other work that's going on in gradual pruning where people are thinking about how can I prune, maybe not at initialization, but at intermediate points in training as well, right? And then as well, they are also seeing this phenomenon at these larger settings, like what's happening? Where's the separation going? Right now, what happens is this. So the sensitivity that we see is as follows. So we have IMP, and I'm going to change IMP to, instead of just being IMP, I'm going to say that this is, if we run IMP with a learning rate or a maximum learning rate during training of 0.1, right? And so this is the setting that we're studying. And this is going to be, let's say, the standard hyperparameter settings for VGG16. Now, if we change the hyperparameters for this problem, in particular, if we lower the learning rate, what we see is this gap now open. So now our orange lines are if we rerun these experiments, but changing the hyperparameters of our experiment, right? Right. And in particular, what we're seeing precisely is this sensitivity to learning rate is what was showing up, right? Now, while we were doing these experiments, we took another step. And the step is that we, instead of just lowering the learning rate, instead we did linear learning rate warm-up, which means over, let's say, the first several epochs of training, we're going to go from a low learning rate up to a high learning rate, right? Where at the end, we're going to reach the top learning rate that we're going to have in our normal setting, right? And so here, these are the green lines. And so what you can see, so what can we see? So one, when we lower the learning rate, we actually reduce the performance at that 100% points. We actually reduce the performance of the network itself, right? We really want to train with higher learning rates when we're working with this particular network and data set, right? So we lowered the learning rate, it gave us the separation. So that's unfortunate. But now when we do the warm up, we recover the accuracy that we have. And as well as our winning ticket phenomena now actually shows up again. So we're seeing this strong separation between reinitialization and our iterative magnitude pruning, right? And so what's happening here? So warm-up, what warm-up is doing is lowering the learning rate through the first initial stages of training. And so now what we are actually seeing in observations that we saw is that there's actually sensitivity to learning rate very early on in training, right? And there's reason to believe that this is the case. So there's been a few papers that have come up in recent years trying to understand the dynamics of training, right? And even showing that there's essentially a two-phase breakdown in the dynamics of training, where the initial phase is highly chaotic, right? Small perturbations to the weights, for example, can send you in entirely different trajectories. Whereas the second phase, where things have roughly started to settle down, and network dynamics or the network training and trajectories become much more robust to small perturbations. Right, so we saw this, we sort of put these genes together, and in our ICML work, what we wanted to do was try to identify a way to measure sensitivity, and measure sensitivity specifically in a way that allowed us to characterize, well, when does iterative magnitude pruning work, right? And when does it not, right? And so that's our question, that's our investigation. And so what we came up with and what we ended up finding was a measure called linear mode connectivity. So there's been some work recently that's happened in the literature on mode connectivity. And the core idea is that if I train a network so there are a couple of different definitions here. So one is if I take two random initializations of a network and then train them, they are connected if I can draw a line between the two copies that does not, where on that line, any network that's on that line does not experience a significant increase in test error, right? And so this is something that's been shown broadly, where I just have two randomly initialized networks. But here what we did is we considered a newer, more narrow definition that actually helped us separate when IMP works and when it doesn't. And so what it is linear mode connectivity. And so here it is. What it is I take a network, a single network, I'm going to clone it. And then I'm going to train each clone with their own seed for SGD. So essentially think about this as each clone being trained with a different ordering of the mini batches as they execute through SGD. Right? So that's one interpretation there. It becomes a little bit more sophisticated to think about, or complicated to think about, if there's data augmentation in play. But essentially the only randomness that we are supporting is in the samples, mini batch samples that we have per iteration of training. And so now what we're going to do is we are going to interpolate between the two copies that we've trained. And there are two things that we might expect to see here, right? They could be connected, right? And here we are considering specifically a linear line. So we are just going to look at a linear line, interpolation line between the two networks, right? And so that's how this is going to be narrower than a much broader, let's say, non-linear characterization of mode connectivity. So again, first one, linear line between two networks. If there's no significant increase in test error along that line, then we're going to say that they are connected, right? They have fallen into the same minimum. And we're going to call this linear mode connectivity, if this is true, right? And now what is the alternative hypothesis? So the alternative thing that we can see is as follows. We can actually see this bump, right? And so what we're going to call this is we're going to say these are no longer connected. They've fallen into different minima according to linear mode connectivity. Now, it may be the case that there are nonlinear paths that connect these networks, but we're explicitly looking at the linear path that connects these two, right? And so this is the analysis device that we developed, right? And in particular, if we look at this bump, the height of this bump, we're going to call this term instability. All right. So this is, again, the analysis device that we developed. And what we did is we then looked at a wide variety of settings. So some of the settings that we had from the original paper, but we also added some additional settings, looking at, for example, ResNet 50 and inception. Right? So now let's look at some plots that look like this, except we're going to apply this to these networks and data sets that we have here. And these are the results. Right? So here on the left, we have IMP Works. So these are settings where IMP works just fine. Right? And if we look at this blue line, what it is plotting the test error as we interpolate from one network to another, right? So the left side of each one of those graphs is going to be one network, and the right side of each one of those graphs is going to be another one, right? And between 0 and 1 is going to be some interpolated network between them where we're measuring test error, right? So in all these instances where IMP works, we can see that this is a relatively flat line. Right. Now, if we look on the other side, however, where IMP does not work, we actually see this disconnection. These are networks are arriving in different minimum according to this linear criterion that we have, right? And in particular, if we look very carefully at ResNet 20, VGG 16, and we look at some of the results that we had in our original paper where we're looking at warm-up, we can see now the difference, right? So remember, what is warm-up doing? Warm-up is essentially lowering the learning rate in those first few phases of training, making it a little bit cooler, a little bit less chaotic. And what we can see is that the result is we're on the right side, that blue line, essentially in the middle of that blue line, we're getting random performance, right? We're on the left side, this is flat, right? So by introducing warm-up, what we actually do, or even by introducing a lower learning rate, but by introducing warm-up primarily, what happens is that now we end up in this linearly connected mode regime, right? So this is the effect. This warm-up, what it was doing is actually allowing us to recover this particular property, right? So just in sum, this initial phase of training is just too chaotic, right? For us to use that high learning rate that we'd have in our standard hyperparameter setting. So we can either lower the learning rate, but then we lose performance, or we can think about using warm-up, right? But there's a little bit more, right? So if it's just this initial phase that's too chaotic, then perhaps we can just consider skipping that initial phase when we think about this, right? And the question that we can ask is, well, do subnetworks become stable later in training? So what we're going to do here is we're going to run a different set of experiments, right? So when we talked about our first set of experiments, what we did is we found this structure at the end of training, and we applied it to the very beginning of training. So we reset it to initialization, right? Applied it to our random initialization. Instead, what we're going to do is we're going to apply this structure to some network that is partially trained, right? At some iteration K throughout training, we're going to apply this structure. So to revisit, we can put this in pictures. So traditional IMP as we had it before. So at iteration 0, we trained fully to convergence at iteration T using our standard hyperparameter setting. We then pruned, and then we applied that to iteration 0, right? All right. So now with rewinding in this new setup, what instead we're going to do is we're going to train to some iteration K. We're then going to take a checkpoint, all right? We're then going to finish our standard training regime, prune, and then we're going to apply that now to iteration K, right? And so now we can ask questions about these iteration K subnetworks and how they behave, right? And so in particular, what we can do is we can now run those standard lottery ticket curves that we've been seeing before. Again, x-axis, percentage of weights remaining, y-axis, our accuracy. And so this blue line is essentially for ResNet 20, the standard behavior that we'd see before if we were applying IMP. So if you rewind to iteration 0, that's the same as if you had just applied IMP as we described before. But now observe, as we increase the rewind iteration, our performance starts to improve. Right? And in particular, once we get to rewind iteration 500, we can see that our performance is now recovered, right? Essentially where we're actually doing quite well. And in fact, it actually saturates, right? So we're actually seeing, as we continue to increase those iterations, those rewind iterations, so we're actually applying this mask to later and later parts of training, we're actually not really seeing a substantial improvement in training, right? So this rewinding, could be the key. What it's telling us now is, iteration 500 for this network is about 1% in the training. So what it's saying is that we can actually now recover lottery ticket-like behavior, right? Essentially where we're able to reduce the size of these networks and still maintain performance if we just wait until 1% into training, right? Instead of going to initialization. Right? All right. So now we can adapt this instability measure that we had. So let's look at this again, right? So instability, remember we started with, for our linear mode connectivity, and then finally instability, we started with an initial point and we trained 2 copies. But instead what we're going to do now is we're gonna start with our initial point. We're gonna take our checkpoint, as we saw before, our purple checkpoint. And now we can train to convergence, we can get a mask, we can apply that mask to that checkpoint. And then we actually test these new networks as well. So we can now test the stability of these pruned networks given some iteration K, right? And again, instability is just going to be this increase in test loss that we see. Now, so what do these graphs look like? So again, IMP works, IMP doesn't work. So let's take a look. So now these graphs just change just slightly big. On the x-axis, we are plotting the rewind iteration, right? And on the y-axis, we're actually plotting the instability, right? And so when IMP works, what are we seeing? So if we're looking at a network, so for each one of these are particular sparse subnetworks of 6.9%, 1.5%, 3.5% respectively, if you look at those top 3 graphs, right? And we're seeing how stable they are in their optimization landscape in particular, right? And what we can see is that when IMP works, these networks are actually stable at initialization, and they continue to be stable even though you choose a later point in training at which to generate these pruned networks. Right now, a good contrast point, so I didn't explain the orange or green lines before, but a good contrast point here is what happens if you were to just randomly prune instead of trying to apply IMP. What happens if you just randomly prune? Well, when you randomly prune, you can see they're actually not stable at all, right? And so these networks that we are finding in this IMP setting seem to be particularly stable in the optimization landscape, according to this definition of linear mode connectivity, right? And so this seems to be what makes these winning tickets to be uniquely suited to train well, or it's release related. We're still, working through the exact causal explanations for what's happening here, but we are finding that these subnetworks are much more stable when you train them, found via IMP, right? Or these subnetworks found via IMP are much more stable than, for example, if you were to just randomly prune to that same sparsity. And this seems to be a key to enabling them to train, right? And the way that we can see this is if we go to this right side of the graph, and in fact, go to this right side of the graph, in the settings where IMP doesn't work, what do we see? At iteration 0, there's high instability for these small subnetworks when we consider them, right? But as we saw just a few slides ago, as we increase this rewind iteration and consider later stages in training, they actually become more stable. Right, so their stability improves. So stability improves means that, or instability decreases. So it means they come down to 0. Right, so we're looking at iteration 500, for example, of VGG16. Right. Now on the bottom line, now we can actually plot this stability versus accuracy. So stability being the top row of plots, accuracy being the lower row of plots. And if we look here on the left side, and so what we can see is these networks, regardless of when you rewind, they're just as accurate as the full network. However, on the right side, when IMP formally did not work, these only become as accurate as the original network when they are stable, right? And so particular, if we look at ResNet 50 down here, it's about epoch 5. This is the point at which we're seeing that stability line come down to near 0 and essentially hold flat, even if I increase the rewind iteration. This is about where if we generate a subnetwork at that point, that is the point where we can expect it to match the accuracy of the full network. So this is what we found. So what's the takeaway here? So the takeaway here is that subnetworks are winning tickets when they always find the same linearly connected minimum, right? And again, this is regardless of the sample of SGD noise, where again, SGD noise is going to be the random perturbations or the randomness that's enabled by the mini batch construction that you're going to have when you train two independent copies of this network, right? So what we're finding is that these are winning when they are stable to this type of SGD noise. Now, in small networks, this occurs at initialization. So those are our initial results, and that's what we saw in this smaller setting. But for large networks, this is happening later in training, right? Potentially 5% into training is what we're seeing for a state-of-the-art network like ResNet 50, right? And so our current understanding here, if we take our lottery ticket hypothesis as we articulated very beginning in the talk and as we articulated even in the original paper, our revised understanding now is not at initialization, but early in training, there exist sparse subnetworks that can reach the same accuracy as this full network, right? And what's nice here is this is very early in training for thinking forward to the benefits that we might get. We're not, if we in principle could find a technique that 5% into training could find efficiently these types of networks, there's a good opportunity to increase the performance of training. So now to take a step back outside of that, and of course we get into the end of the talk, end of the hour. There's been a number of implications and follow-up that's come out of this work. So there's several papers I'd just like to highlight, but there are many more that are out there. But some of this work, as Farhan had asked about before, is actually looking at and investigating transfer. One, can I essentially transfer these networks to different data sets? Or alternatively, does this just exist for settings outside of vision? And so the answer to both of those is yes, based on some of the work that we've done, but also some of the work by others that are out in the community. Right? There's also been very interesting work on studying more of this phenomena to see if we can get a better characterization of what's going on. What are the actual semantics? What do these masks look like? Can we propose training procedures that just learn masks, right? Which is an interesting thing that shows up in these top two papers on the left and the right. Right? Right. And then finally, as well, we've been doing some work in actually taking some of the observations here and actually using it to design new procedures for generating efficient networks just for inference. Right? And I'm happy to talk about those in the time after the talk. But as I promised, returning back to this particular question, can we find these subnetworks efficiently? What I want to do is just, so we are looking, we're searching for a better technique. And we have some good leads that we're moving in. But what I wanted to really give you a preview of is just the current state of the work as is, right? When you look broadly across the community, and in particular, how we can assess what success means and what the lottery ticket hypothesis tells us about the opportunity so far. And so the way I want to organize this is as follows, right? Where what I want to plot here is the number of weights that are remaining as a function of the epochs of training for here ResNet 50. And so the design here is, this is essentially the best known number of weights that we can keep at that given iteration for a given technique and still roughly match the behavior of the original full network, right? So unpruned, this is just our benchmark. This means we maintain 100% of the weights throughout training. Nothing surprising there. There's been some very interesting work on gradual pruning, or what people have done is identify that about a third of the way through training, you can use a variety of different sparse learning techniques to reduce the number of parameters according to a schedule, right? So this is some gradual pruning work that's come up. Now, as I mentioned before, random pruning for very overparameterized networks can actually work, but it does not get you very far. Depending on the setting, you can get maybe between 60 and 80% of the parameters removed with random pruning for a very overparameterized network. Right now, the lottery ticket, as we've seen, what it articulates is that perhaps the limit is this, which is about 5% into training. If we can find these, then we can drop down to 10% of the size of the original network and then continue training. It's essentially the lottery ticket observation. So this is really the remaining opportunity, right? From where we know we are right now, and I'll revise that in a second, to where we'd like to be. And there's been a few papers out in the literature that have tried to articulate new ways for improving the state of the art. And so far where they've gotten is about here. So this black line, somewhere around 50%. So there's still a significant gap from what's known and what's done to where we'd like to be based on our results. And so this is the direction that we've been moving going forward. And so, be on the lookout for work from Jonathan, trying to push this bar even lower, over the next year. So the takeaway here, now that we're right at time, I'll take questions after if you have some opportunity to be around for another 10 minutes or so. But early in training, this is the key current observations that we have. There exist these sparse subnetworks that reach the same accuracy as the full network. And their implications, fairly widely. We talked about transfer, but also hopefully for standard learning, really if we can develop new methods. Right? And I'd say, looking forward, there are just open challenges for new methods, open challenges for new software hardware systems that allow us to accelerate this. And then finally, open challenges for theory. Right? Really, can we prove things in this space? There have been preliminary efforts, but no breakthroughs, I'd say, so far. Right? And so that's it. Happy to take questions.
Thanks a lot for the talk. If you have questions, feel free to unmute yourself, or if someone else is talking, you can raise your hand and I will call you up.
Sure, I'll jump in. So I'm curious how much of a computational gain can you get from this, right? So it seems very interesting that you can stop at sort of like 5% and cut down a lot on the number of connections in the network. But I could imagine that you might even not need as much data to train the remainder of the network because you now have fewer connections to be training. Do you see any kind of that behavior emerging in your results?
So, and I'll also let Jonathan peek in on this one as well. So this is a question that we're actively trying to understand. Essentially the relationship between data efficiency as well as pruning. And so we have just started to articulate some of these questions. I'm not aware of anyone who has answered that particular question quite precisely out there right now. It is our hope that I got a thumbs up from Jonathan as an accurate assessment of the state of the work. But our hope is that there may be some data efficiency gains just because these networks are smaller. But it's an open question, so perhaps get back to us in about 6 months.
Thanks.
I have a question in the continual learning setting where you're continually learning tasks. Would it be feasible to have something like the lottery ticket, or because there is this critical regime at the beginning of learning, the lottery ticket does not apply in this setting?
In the continual learning setting. So here, I mean, I'm not sure if continual learning would conflict with this idea. I mean, and just to clarify here, this is a setting where, for example, what I talked about, where daily I'm having changes in distribution. I'd like to be able to incorporate that into my latest model, right? So I do think there'd be essentially same observations in the sense that this initial stage you need to be mindful about, but ideally, once you've identified the subnetwork, you would be able to use it, say, in the continuation. Now, where I would be concerned is if there was significant data drift between day to day, right? If so your continual learning model has significant drift in data over time, one, I mean, this is just gonna be a challenge for any technique, but I think getting to your point, this may bring into a good question of whatever was done in that initial stage of learning, does it need to be redone? It's a very good question. I don't know.
Awesome. Are there any other questions?
Hey, Michael,
Hey,
I had another question.
Yeah, go ahead.
Did you get any of the lottery ticket observations to work on structured pruning for larger networks?
I don't think we have seen any of that for structured. We had an iClear paper this past year where we looked at, we're actually looking at the inference setting for those. And I don't think even in that enumeration did we see anything interesting for structured. Jonathan can put in.
This is where I'm going to take my prerogative and jump in. So the Rethinking the Value of Pruning paper is largely about the structured setting and shows, in fact, these observations don't apply. You can randomly reinitialize. So there's this interesting dichotomy between sparsity and pruning in a structured or dense way, pruning, neurons in the representation space. So I think this remains one of the most interesting open questions: is why sparsity? Is there something natural to the functions that get learned? Is there some inductive bias to SGD? Is there something to the way that we structure our architecture such that we see these interesting properties in the sparse regime, and we see we can prune many more weights in the sparse regime than we can in the structured regime? I don't have the answer to that, but I think this is one of the big open questions in my mind, and I would love to find a way to evaluate it.
Well, thank you. So maybe it seems that having less features immediately hurts accuracy, but maybe weights within features are not necessarily important to produce the features.
Yeah, so it's actually, I mean, this also even brings up another result that we've seen recently with the SynFlow work. Right? So I don't know if you're familiar with SynFlow, which just showed up on the scene in the past few months, but it's another pruning at initialization technique. And in some of the results that we just put out on archive in the past few weeks, we found that this technique, although it has a unstructured pruning metric, so it prunes per weight, once you apply its pruning fully, you find that it eagerly removes all the weights for a neuron. So it effectively devolves to structured pruning at some limited level. Right? And so what we found, though, is then if you take the per layer sparsities that SynFlow identifies and then just reshuffle the weights, the mass that you have, essentially to now introduce this unstructured sparsity, you actually improve performance quite substantially. Right. So, these observations, as Jonathan is pointing out, it is very much tied to this idea that perhaps, it does not make sense to entirely eliminate features, but you can perhaps reduce, let's say, the resolution of a feature and still have it be useful. Right. And this is the current hypothesis that I have in my mind. Right? And so unstructured pruning allows you to get that reduction in resolution without a full collapse in the feature.
Thank you.
There is a question on YouTube by Divya Kulkarni, who asks whether there is a relation between the lottery ticket hypothesis and neural architecture search.
Ooh, always a good question. So this is essentially one of the core arguments behind the rethinking the value of pruning, where what they tried to articulate is if you look in the structured setting, there's really no gain to try to use some of these iterative magnitude pruning techniques. And instead, if you just randomly initialize some architecture that's smaller, then it will work just as well, right? So I would argue that they do articulate a quite close connection between neural architecture search, and I'm happy to think about that. I'd say in the structured pruning setting, which is what they thoroughly evaluate in the entire extent of their claims in that paper, is all for structured pruning. But I think for unstructured, it is a very good question, right? I think you can make a connection in the sense that at the end of the day, we do find some sparse architecture that works well. I think the real question is, what is the full search space that you have, and can you articulate that well in a way that matches how we think about pruning? I don't know, Jonathan, do you have any other additional comments on architecture search?
Yeah, the one thing I'll say about that is architecture search over sparse networks is an extraordinarily large search space compared to anything else that neural architecture search might consider. Ideally, we'd do some kind of search, find the ideal sparse network, and then use that going forward. But that problem's infeasible, and at least given our current computation available. And so the best we can do is to try to prune using these rough heuristics. If we could do architecture search over the space, I'm not sure we would even be doing pruning. That's at least my rough diagnosis. Structured pruning, you're dealing with the widths of the layers. And so as Mike said, you can, it's a little bit of a smaller design space to explore.
Awesome. Are there any final questions?
I have a question about, was there any correlation between sparsity of activation and pruning? Like, for example, as weight of model get pruned, the more sparsity appears in activation functions like ReLU?
That's a good. So I don't believe we've analyzed that in the lottery ticket work. So in some work that I actually did when I was working with Microsoft Research back in, this would have been 2015 or so, we did actually develop some new systems that exploited activation sparsity. And what we found is that networks naturally became activation sparse over time, right? So as over time, what I mean by over time during training. So while activations may be relatively dense at the initial stages of learning, by the time you get to, let's say, halfway through training, they're actually fairly sparse, and the sparse structure and activation emerges. And so for me, what that closely corresponds to then is some of this work that I briefly mentioned around gradual pruning. And so while I haven't investigated it, I might guess, right, that these two are closely coupled, and you might be able to run experiments to demonstrate a connection between the two.
Okay, thanks.
Awesome. So it's quite a bit past 3 p.m. So let's leave it here. Thanks a lot, Michael, for coming.
Yep. All right. Thank you. Thanks for having me.